And we are live. Okay, welcome to Math with Doug. Here's the dog. We're starting a new topic, which is pre-algebra. So it's really beginner approach to algebra. Everyone should be able to understand, even you, if she can stay awake. Okay, I'm going to put her down. Lie down. Stay. Good girl. Okay, I'm wearing a Barcelona shirt, one of my favorite shirts, and it's really nice out. Nice spring weather. I'm enjoying myself. I might even be cooking something on the barbecue for supper after I finish this. After I finish this, first I have to give her her supper. Then I can cook my supper on the barbecue. Priorities. Okay, so pre-algebra, we have to cover a bunch of topics that the students have to be familiar with and comfortable with in order to get started with algebra. Because when we do actual algebra calculations, it's assumed that you know certain stuff. So we just do a bit of a review to start with. And one of the things that we're reviewing is factoring. And we're going to factor one of my favorite numbers to factor, which is 24. Because 24 is one of the smallest numbers that actually has quite a few factors. It makes it a good example. What is factoring? Factoring is kind of the opposite of multiplication, because when you know how to multiply, you will multiply two numbers and you'll get an answer. Factoring is kind of like being given the answer and said, okay, what was the question? What numbers multiply to give 24 in this case? And there's different types of factoring, all of which are useful. So we have factorization that I'm going to do here. We have prime factorization, which I'm going to do there with a factor tree. You may have seen one of those before. And then there is this type of factoring that I don't really know a particular name for, so I call it the onion, or rather layers of the onion. But I'll get into that. What I want to start with is factorization. And what I'm doing is I'm giving the answer 24, and I'm going to write down the question, two numbers that multiply to give 24. But there is more than one correct answer, because 24 is not a prime number. It has more factors than just the ones every number has, which are 1 and itself. I'm going to start with those. 24 is equal to 24 times 1. And that works because 1 and 24 are both factors of 24. We know that's true because 1 times 24 equals 24. But they're not the only factors. So what other two numbers besides 1 and 24 can you multiply together to get 24? How about 2 times 12? 2 times 12. Notice how I put the bigger number first here, and in the second example I put the bigger number second, because it doesn't matter with multiplication. 2 times 12 is the same thing as 12 times 2. They both give the same answer. They both give 24. So we have now found these two factors that are factors of 24. We have found these two, and there are more. I listed 4 24s because there are 4 different pairs of factors that can be used to give 24. And of course, if you know your multiplication tables, then you know these. And that's another reason why I like using 24. It's a nice, easy number, so even a student who's only part way through learning their multiplication tables is probably already quite familiar with 24 and all the numbers that multiply to give 24. That kind of helps make this easy when we start factoring. So I tried 1 and it worked. I tried 2 and it worked. That's one of the things I do when I'm factoring, is I try the various numbers that might be factors and see if they work. So after trying 1 and 2, it kind of makes sense that I'll try 3. So 3 does work because 3 times 8 is equal to 24. There's only one more pair. You notice how the 1 and the 24 are really far apart, and 2 and 12 are actually closer together, and the 3 and 8 are also closer together than that. That kind of happens with factoring, but then we get into the layer of the onion thing, which I'm not talking about yet. Okay, so what other two numbers? There's only 2 more. There's only 2 other factors of 24 besides the ones I've already used. So I tried 1, I tried 2, I tried 3. So obviously the next one I would try would be 6. Yes, 6 times 4. You thought I was going to say 4, didn't you? Well, I did, because 6 times 4 includes 4. I don't have to say the 4 first. We already talked about that. 6 times 4 is the same thing as 4 times 6. Yes, 6 times 4 equals 24. I did it. I did factorization. What I did this time was I listed all the possible pairs of numbers that I can multiply to get 24, which means I listed all of the factors of 24. Aha. But then another way of doing this is the layers of the onion. I just wrote the word onion, but I always call it the layers of the onion. Because I think of an onion, and when you cut up an onion, you realize that it's got this outer layer, and then there's an inner layer, and then there's an inner one. It keeps on getting smaller and smaller, the onion, until you get to the innermost layer. So I kind of think of that when I do this type of factoring. What I do when I do this type of factoring is I start with 1, because 1 always works. 1 is always a factor of every other number. But then I say to myself, what do I multiply 1 by to get 24? And I realize, well, it's going to be 24. So 1 and itself will always work with every number, even prime numbers. But I don't want to write the 24 right next to the 1. I want to write it really far down, and I'm sort of guessing about how far to put it. And I put a comma after this one, and I put a comma before that 24, because any other factors that I'm going to find are going to go in between. And then I try 2. So it's kind of a similar strategy that I was doing here. Try 1, it works, then try 2. If it's an even number, it's going to work. 24 is an even number, so yes. 2 times 12 gives 24. I write the 2 next to the 1, I write the 12 next to the 24, and I put a couple of commas so that I'm ready for more numbers. Then I try the next thing after 2, which is 3. 3 times 8 does give 24. It's working. And then I try 4. 4 times 6 gives 24. I don't have much room left. The only thing I would be able to put in here would be a 5, but 5 doesn't work anyway. 5 is not a factor of 24. So I don't really need 2 commas. I guess I could get rid of one of them. There, I'm done. So that's what I mean when I say I kind of guess how far I should write the 24 after the 1. When I know a number has a lot of factors, I give more space so that I can write a lot of factors. And when I know a number has very few factors, I don't give as much space. But it is a little bit of guesswork sometimes. So the layers of the onion, the innermost part of the onion, I guess, is the 4 and the 6. And then the outermost layer, that's, you know, kind of brown and chewy and you don't want to eat it, that's going to be the 1 and the 24. I have used the factoring method, layers of the onion. I have factored in 2 different ways, which have a lot in common. And then there's this one, prime factorization, the factor tree. Probably the funnest thing that you could do. This is an example of something I've said many times. There should be puzzle books that you can buy in the bookstore at the airport or the train station, where all you do is do factor trees, because they're so much fun. You'd have a book with lots of pages and factor trees for all sorts of different numbers, and you start with the easy ones and eventually move on to more challenging ones, just like any puzzle book would do. Okay, with prime factorization, one of the things that's fun about it is I can choose any 2 factors of 24 to start with. It doesn't matter which ones I start with. So I can try and make it interesting by saying, you know what, I think I'm going to try starting with 3 and 8. 3 times 8 gives 24. And you see the 24 is showing that it can be made up by multiplying a 3 and an 8. But then you have to keep going. And then it starts getting interesting because 3 is prime. So I can't break the 3 down into smaller factors. But 8 is not a prime number. I can break it down into smaller factors. So what I do with the 3 is I just write a little line and I continue it down to the next line. And then for the 8, I'm going to split it like I did with the 24, and I'm going to write down 2 of its factors. And again, I might have choices. We don't use 1 when we're doing this. It just goes on forever if you try to use 1s. So 8 is 2 times 4 or 4 times 2. I can write it either way. I'm going to write 4 times 2. And then I'm putting the multiplication symbols. But I'm not finished because 2 is prime, 3 is prime, but 4 is not prime. 4 has factors, and therefore I carry down the 3. I split the 4 into its only factors. The only choice I have is 2 times 2, and then this 2 I also carry down. So now we see what are called the prime factors of 24, which is a 3 and 3 2s. That can happen, it's okay. Once you get to a list of factors, all of which are prime, you're done. And the amount of branches in the tree depends on how big the number is and how many factors it has. It's fun. And I think what I'm going to do next, I'm nearly finished with the factoring part of this lesson. but I do have a bit more time I wanted to spend on it, so I think what I'd like to do next is do another factor tree of 24. I want to do it again, but I want to try and do it differently. Yeah, so I'm going to erase this stuff, and I'll do another factor tree for 24. First, I'm going to take a sip of my fizzy water. Vanilla cherry soda flavor. Okay, eraser cloth. Erase, I'm erasing the word onion. I'll leave factoring the number 24 up there because I'm not really finished doing that. I'm erasing all of this. And I have room now for another factor tree, maybe two more, we'll see. How many different factor trees can I do for the same number? It depends. It depends on how many factors the number has. So I'll put one here and leave room to do another one, and we'll see. So what I want to do is I want to do it differently, which means I'm not choosing 3 and 8 to start with. I'm going to choose anything else I want. And we remember all these factors we were talking about. How about 6 times 4? And then we do the same thing. Okay, what's the factors of 6? What's the factors of 4? And we show the branches and we write them. 6 I can get by doing 2 times 3. And 4 I can get by doing 2 times 2. I need another multiplication symbol. Oh, and I'm finished. So I only went down 2 sets of branches this time, and I went down 3 sets of branches that time. That's kind of interesting. Can I do it yet another way? I got the same answer. 2, 3, 2, 2. 3, 2, 2, 2. What matters is there's 1 3, and there are 3 2s. So I have all the prime factors. It's the correct answer. It just looks different. How about trying it a third time? I'll leave room for a fourth. Maybe I need a fourth. I'm not sure. And I want to choose anything else. I've used 3 and 8, and I've used 6 and 4. So I guess there's not much else to choose except 2 times 12. Because like I said, you don't want to use 1. Because if you try to use 1, it just goes on forever. Maybe I'll use that space to try that, just to show how it goes on forever. 2 times 12, 2 is prime. I'm just writing another branch line and carrying down the 2 onto the next line. But 12, I'm not finished. 12, I have choices. I can do 3 times 4, or I can do 2 times 6. So let's say I do 2 times 6. Okay, but I'm not finished. This 6 is not prime. So this 2 I'm carrying down. This 2 I'm carrying down. But the 6, I am turning it into a 2 and a 3. And I'm putting that extra multiplication symbol, and I finish 3 2s and a 3. Same answer as the other ones. So I realized that, yeah, there is a fourth different way of doing this. Can't do this any differently. Can't really do this any differently. I could write 2 times 4, but we already know that's the same thing as 4 times 2, so it's not really different. But when I factored the 12, I used 2 times 6, but I could have used 4 times 3, so I'm going to do that instead. Well, I'm going to do that also. So here's 24, and I think just for variety, I'm going to write 12 times 2, same thing, but I put 12 first. And then I'm going to carry down the 2. Splitting the 12, I did 2 times 6, so I want to do 3 times 4. And again, I have the 4. I have to break it into its factors, which is 2 times 2. I'm going to carry down this 3, carry down this 2. The 4 is turning into 2 times 2. Put the missing multiplication symbols, and I have 3 2s and a 3, just like with all the other ones. I think I have exhausted all of the options. I can't think of anything else I can do that doesn't just repeat one of these 4. I've used up all the space, so I don't have any room to do that one where I try the 1. So what I'll do is I'll erase everything, and I'll do it one last time, and I'll use a 1. This is just to entertain myself, and hopefully to entertain you. I'm even erasing the phrase prime factorization. So this will be a fast one because it's just silly. I'm going to put the 24, break it into 1 times 24. 1 is prime. And the 24 I can break it into 1 times 24. 1 is prime. I better write my 1s like this so that it's easier to see that I have 1s. Another problem with using 1s, this one I'm carrying down, and the 24 I can break it into, well, this time I'll write 24 first times 1, and I put a multiplication. Okay, so you realize this can go on forever. which is why we don't do it. So when you do a factor tree, you don't bother writing 1 times the number you're factoring because it would just go on forever. It's kind of fun in its own way, but I think it's more fun to just say, I think I'm going to take another example and do one more, but with a different number. That'll give me some variety. So I'm going to do that. Let's see, my lesson plan, I'm looking at how much time I have for each topic. And I actually still have a bit of time. And I think more examples is always better. So, 24 was fun. It's one of the fun ones. I'm going to try, I'll try something that doesn't necessarily have huge number of factors, but that's still fairly big number and it tests your knowledge of the multiplication tables quite well. How about 120? Yeah, that's in the multiplication tables. And there are all sorts of choices, right? So we could choose, we're not choosing 1 times 120, but we could choose 2 times 60. We could choose 3 times 40, but we'd also choose 2 numbers that are both in the multiplication table that goes up to 12 times 12, which would be 10 times 12. Haha. So I just feel like doing that. And then 10 is not prime. I can break that into 2 times 5, but both of those are prime. And then 12, we've seen this one before. I can break it into 3 times 4. And I'm almost finished, but not quite. 4 is not prime. So I have to copy down the 2, copy down the 5, copy down the 3, and then take the 4 and break it into its factors, which is 2 times 2, and put in my multiplication symbols. 2 times 5 times 3 times 2 times 2 has to give 120. Let's test it. 2 times 5 is 10, times 3 is 30, times 2 is 60, times 2 is 120. It's working. So this one has 3 2's and a 3 like 24 did, but it also has this 5. Wow, it's the same prime factors as 24, except with the addition of a 5. And it just so happens that 5 times 24 is equal to 120. The way everything just works so beautifully is one of the reasons I like doing this so much. Fun. A fun type of math. Another one. I do still have a bit of time. I could do a couple more examples. I don't want to do crazy, ginormous numbers, but I'm trying to choose something different. How about 84? Yeah, 84. And again, that is an answer in at least one little corner, or 2 little corners, of the 12 times 12 multiplication table, because 7 times 12 is equal to 84. That's 12. Boy, we keep on seeing lots of 12s. That's just maybe the coincidence because of which numbers I happen to be choosing, which I'm doing kind of randomly. But 7 is prime, so I'm copying it down, and 12, I'm choosing this time to do 6 times 2, and 7 and 2 are both prime, so they're both being copied down, but 6 is factors down into 2 times 3, and I put my multiplication symbols, and I have 7 times 2 times 3 times 2. This time I have 2 2's and a 3 and a 7. So all sorts of interesting stuff happens. But the important thing is at the end you have all of the prime factors of the number you started with, and that is kind of fun. Right next to it without erasing. A prime number. I'll do it. It's not going to take long. How about 5? 5 is prime. And all I can do is break it into 1 times 5, which means I may as well not even bother with a factor tree, because it's just pointing out the obvious, and then we get into that repeating as many branches as goes on forever, where we keep on getting a 5. Okay, that wasn't as fun as I thought it would be. How about 27? 9 times 3. It's really the only choice. 9 times 3 or 3 times 9, which are the same thing. 3 is prime. 9 breaks down into 3 times 3. Oh, this is one of the cool ones that gives you a list of prime factors at the end, but every single one of the prime factors keeps on being the same number. And then we could get into all sorts of interesting math stuff where we say 27 is the cube of 3. that sounds like it should be part of last week's lesson, where we had the volume of a sphere, which had the radius cubed in it. 3 times 3 times 3. If the radius of a sphere was 3, we would have 3 times 3 times 3 as part of our solution when we find the volume of that sphere. Interesting. But that's enough for the factor trees, and in fact it's enough for the factoring altogether, because I want to move on to some other ideas. Types of numbers. That's an interesting other idea. Natural numbers, whole numbers, and integers. And we're doing all of this because we want to move on to doing algebra. And knowing these types of numbers, natural numbers, whole numbers, and integers, is useful because when we get into algebra, we're going to use natural numbers and whole numbers, which we're used to using, but we need to also be able to use integers. We can't really stretch our algebra muscles unless we include the integers, because they happen in algebra just like other numbers happen in algebra. Okay, so what are natural numbers? What are whole numbers? What are integers? Natural numbers . These are the numbers that we learn first when we're just starting to learn math. We learn to count. So the numbers you use when you're learning to count, those are the natural numbers. They are 1, 2, 3. We're not using 0. 0 is not included in the set of natural numbers. And yes, I can express it as a set if I want. It would look like this. And since it goes on and on, after 3 you have 4, then 5, then 6. It's hard to, you can't really list all of the natural numbers because it would take forever because they go on forever. But you could also do it this way. You're basically saying, okay, the set of natural numbers is 1, 2, 3, 4, and it goes on and on. So if you know how to count, you know what it means. And then there's the whole numbers, which is the same thing, almost. The whole numbers are the natural numbers, but they also include 0. So 0, 1, so you're counting, but you include 0. And anyone who wants to, when they count, could decide to start with 0, right? 0, 1, 2, 3. Otherwise, it's the same thing as what we were just doing. So there's the natural numbers, there's the whole numbers, and that's the difference between them. It's not a big difference. It hardly ever comes into play and matters when you're doing some math, but it's still good to know. And then there are the integers. Making sure that it fits into my video rectangle. Integers, which is like the whole numbers, but also includes negative numbers. Okay, so that means it's like the natural numbers, but it also includes 0 and the negative numbers. So that, I want more room, would be a set. This set is a little different for drawing. I'm going to do the 1, 2, 3, ... thing, but over here I'm putting a 0, and then I'm going to show -1, -2. I ran out of room, so I put my ... So basically it's counting up 1, 2, 3 forever, but also down 0, -1, -2 forever, in a way that's useful, for instance, when you are working with temperature, because temperatures can go into the minus temperature, they can go into the negative numbers. If it's very, very cold where I live, in the Fahrenheit scale, you have negative, in the winter, you have negative temperatures. And if it gets really cold, we're talking about -25, -30 Fahrenheit, these are cold temperatures. So when you deal with temperature, you put yourself in a position where you have to start using integers. But also when you learn algebra, you also start learning integers. Okay, that's enough for the numbers. I just wanted to remind the students of the different types of numbers. And now we're going to work on, what did I have here? Aha, adding and subtracting when it involves integers. So of course all of the students know how to add and subtract with whole numbers and natural numbers. But eventually the student will get to a point where they also have to be able to add and subtract with integers. So negative numbers start to be involved. And we just have to learn a few rules and we can do it. So what happens, okay, I'm going to start with something easy. What happens, let me take a look at, I'm going to keep my clipboard with me now. When we have two positive integers. Okay, well if they're positive, then it means they're integers, but they're also natural numbers, they're also whole numbers. So it means that's like a question for more beginner math students. So I started with something easy. I said I was going to start with something easy. How about 7 plus 4? What rule do we apply when we add two of these? 7 plus 4 equals 11. So we add them, and it keeps the sign of the original numbers. When we start with two positive numbers and add them, we're always going to get a positive answer. So I can put a plus sign just to, point that out. And that's kind of a fast one. Can do a couple more examples. Any two positive integers. So 3 plus 31. That's going to give me positive 34. I'm just adding the two numbers, and then because they were both positive, the answer is going to be positive. So there's not very much to that. But wait, what if they're both negative? Okay, now we have some stuff to do. How about negative 5 plus negative 2? When we do this, we add the numbers, and then they're going to be negative. So it's kind of the same thing. Both of these were positive, so we added them, and the answer was positive. Both of these are negative, we're going to add them, and the answer is going to be negative. It works. So let's do another example. Negative 6 plus negative 3. 6 plus 3 is 9. The answer is going to be negative. So this is something that's worth practicing if someone's new to it, but it is also something that gets to be really quick once you have practiced it a little bit. So if it's not quick for you, practice it. Good idea. Okay, what if you have a combination of a positive and a negative? This is where the work starts. So I have negative 2 plus 8. So the first number is negative, and the second number is positive. How do I do this? When I have a negative and a positive being added together, what I do is I subtract instead, and then I give the answer the sign of the bigger number. Now we have a rule, right? So 8 and 2, when I subtract 8 and 2, I get 6. And then the bigger number is the 8, and it's positive, so that means my answer is positive 6. It worked. Negative 2 plus 8 is equal to positive 6. Another one, negative 4 plus 4. Oh, wow, I did something. No, I don't want that one. Sorry, bad example. We'll get to that example later in the lesson, though. Negative 4 plus 9. Okay, so again, the first one's negative, the second one's positive, and I'm going to subtract instead. So 9 minus 4 is equal to 5, and then the bigger number is the 9, and the 9 is positive, so therefore my answer is positive 5. That's interesting. I'm going to end up erasing some of these other ones and talking a little bit more about tricks I like to do when I combine negative and positive integers like this. But it is worthwhile to learn that rule and then just practice it enough so that you will always be able to apply it. You're going to find it easy to remember if you practice it enough. But wait, what if the first number is the positive one and the second number is the negative one? I need more examples. Okay, how about 3 plus negative 12? Okay, so 12 my number got a little bigger, but it doesn't matter. We're just going to apply the rule, and the rule is the same. We're going to subtract instead. 12 minus 3 is 9, and then we're looking at the sign of the larger number, which is the 12, and that's a negative, so my answer is negative. And it works. It gives the correct answer. So there is a rule that you can think of and sort of say in your head when you're doing these. Okay, how about if I have negative 10 plus 6? Okay, I went back to having the negative number first. Does that mean I'm going to get a positive answer? Because in both of these examples where I had the negative number first, I got a positive answer. But that isn't really the rule. I didn't say, whatever the negative number, if the negative number is first, you always have a positive answer. That's not the rule. What I said is, we have one negative and one positive. We subtract instead. 10 minus 6 is 4. Then we see which number has which is the larger number, and it's the 10, and what is the sign of that number? The 10 is negative, the larger number is negative, so my answer is going to be negative. So it still works. You don't have to have a smaller negative number plus a larger positive number when you apply this rule. You can have a larger negative number plus a smaller positive number, and the rule still works. So the rule is designed to be flexible and to be able to handle any combination. So larger, smaller, smaller, larger, negative first, positive second, positive first, negative second. None of that matters if you apply this rule. It just always works. So it's really, this is the same rule as that one. How am I doing for time? Quite well. I think I should do some more examples of these. What can I do? I think what I need to do is just sort of randomly give combinations, and let's test whether we remember the rule that we're applying so we can get the right answer. So I'm going to erase all of these. We're going to just have to remember the rule. I did not write down the rule. Writing paragraphs like that is kind of slow on the chalkboard wall. Okay, how about, and I'm sort of randomly choosing numbers. -3 plus -2, how about 5 plus 6, how about -10 plus 1, how about 12 plus -14, numbers are getting bigger, but the rules still work. How about 8 plus -2? I may even be using some examples I already used because I already forget some of the ones that I've used. But I may have room for 6, so I'm going to do one more. How about, let's do a challenger one. 100 plus -110. There. Okay, so -3 plus -2, they're both negative, so the answer is going to be negative, and we just say, okay, 3 plus 2 is 5, but the answer has to be negative. It works. Okay, 5 plus 6, they're both positive. The answer is going to be positive. 5 plus 6 is 11, and the answer is positive. It's positive 11. -10 plus 1, one is positive, one is negative. It doesn't matter which one's on the left or which one's on the right. It doesn't matter which one's bigger, which one's smaller. I just realize I have a negative and a positive that I'm combining. So I subtract instead. 10 minus 1 is 9. Then I check to see what is the sign of larger number, and it's a negative. So my answer is -9. 12 plus -14. Closer together, but 14 is still bigger than 12. One's positive, one's negative. So I subtract instead. 14 minus 12 is 2. The larger number is the 14, and it's negative, so my answer is -2. 8 plus -2. One positive, one negative. Subtract instead. 8 minus 2 is 6. The larger number is the 8, which is positive, so my answer is positive 6. I really suspect that that's an example I already did. Okay, and then 100 plus -110. One positive, one negative. So I subtract instead. 110 minus 100 is 10. And then the larger number was the -110, so it's going to be -10. My answer is -10. The rule works, and it works really well. And then these rules, both negative, negative answer, both positive, positive answer. That works really well as well. We're applying laws of signs, meaning signs, S-I-G-N, negative sign, positive sign. There are rules for how we deal with numbers when they have negative signs and positive signs, and that's what we're working on right now. When we do algebra, we're going to be needing to apply these rules as a little step as we're on the way through a bigger problem. We don't want to be too distracted by the laws of signs while we're doing our algebra. We want to practice this stuff a lot so that we become really quick and fast at doing it and accurate, and we feel comfortable with it. And then when we're doing a bigger problem that involves the algebra steps we're learning, we'll be able to apply the laws of sines when we need them. That's the point. That's why we're doing this little part of this lesson, this review. One other thing I feel like doing is to do that temperature thing again just a bit. Because when a student struggles with the laws of sines, with adding and subtracting positive integers, one of the things I'll encourage the student to do is use the number line. So let's do a number line over here. I like to put a 0 on my number line. Some number lines you don't really want 0. You want numbers to be way positive or way negative. But most of the time I like to always show a 0. And I'll show 1 and 2 and 3. -1, -2, -3. Okay, and this continues onwards, right? So I put an arrow here if I want. Put an arrow here. Okay. Let's do an addition of integers problem with a mixture of negative and positive where we use the number line. So what if we do -4 plus 7? Oh, my number line's not large enough for that. So what I'll do is I'm going to make my number line a little larger. There is room. I'll go a little higher with the 3. I'll go past the 3 and I'll show the 4 and the 5. And yes, it does keep going. And then over here, -4, because I want to show -4 because it's in my, I'm starting with that in my question. -5, okay, I should be okay. And then I'll make my arrows look like, okay. So -4, that's here, so I'm here. But I'm adding 7. That means I'm going to go that way. But wait, why am I thinking of the number line? I could think of the rule. What is the rule again? Oh yes, one's negative, one's positive. We subtract instead. 7 minus 4 is 3, but the answer has to be +3 because 7's larger. So therefore, it's going here. And then it's really easy to see what I'm doing. Yes, I'm adding 7, which means I'm going in that direction. And 1, 2, 3, 4, 5, 6, 7. Yes, it gives me 3. This is just a different way of visualizing it. And I guess I fill these in because I'm about to erase anyway. Okay, I'm going to erase and I'm going to do a similar thing where I'm going to apply the rule, and instead of using a number line, I'm going to use a thermometer. I like the thermometer because the thermometer basically is a number line. So when I draw a thermometer, I tend to like to draw it so it kind of looks like a thermometer. So the thermometer will have 0 on it somewhere, and I'm just going to choose to put it in the middle. And then you have, it's hard to label all of them. I'll just won't use numbers that are very large in my question. Or should I? Okay, I'm going to use numbers that are small in the question so I don't have to draw too big a thermometer. There's 1, there's 2, there's 3, and there's -1, it's a 1, there's -2, there's -3. These lines on the thermometer are showing me that. I don't know if thermometers really look like that. I think it would look better if I did something like this. There. Yeah, thermometers tend to look kind of like that. Okay, and what if I do 2 plus -4? Okay, so I'm starting at 2, that's here, and it's getting 4 degrees colder. That's the trick, right? I think a number line helps, but a thermometer helps more because you can think of colder and warmer to help you understand what's change is happening. It's getting 4 degrees colder. That would go down by 4, wouldn't it? It's going to work, but I'm going to apply the rule that we talked about. We have a positive and a negative. We're combining them. We're adding them. That means we subtract instead. 4 minus 2 is 2. The larger number is the 4. It's -4, so my answer is -2. That means my answer is going to be here. If it's 2 degrees and it gets 4 degrees colder, yes, it ends up being -2 degrees. It's a cute trick that I like. I don't like the double arrow. It's a cute little trick that I like to help make students think about what they're doing when they're dealing with integers, because thermometers and temperature has opportunities to have negative numbers. And some other things that we're used to doing with math, there's never really any reason to have negative numbers. The thermometer is a good trick for that. Okay, so that's it for that. That's the end of that part of the lesson. I have to turn over my page. And yes, I need another sip of that fizzy water. Properties, a bunch of properties of addition. Yeah, addition. It's mostly about addition, but there's a little bit of subtraction in there too. Okay, so we're going to get into that. The identity property of addition. Okay, I have to do a bit of writing. It helps if you use the end that has the chalk. Identity. I'm putting it nice and high so I have room to put more than one of these properties. Property of addition. Okay, so what is the identity property of addition? It means that if you add 0 to a number, you just get the same number as the answer. You might think, well, that's obvious, I already knew that. Well, I actually expect most of you to have already known that. So we can show it in a sort of a general way by saying a plus 0 equals a. But wait, what if you add a and a 0, but you have 0 first? I want that example to show us first. 0 plus a also equals a. Let's do it with numbers though. What if a is, well, we're not going to say what a is, we're just going to use numbers instead of a. So 3 plus 0 equals 3. I'm just applying the identity property of addition. 3 plus 0 equals 3, because when you add 0 and you add nothing to a 3, you still have a 3. It kind of makes sense. But of course, 0 plus 3 is also equal to 3. Whenever you combine 0 and a number with addition, you're going to get the number that you started with as the answer. But wait, what if it's a negative number? Negative 4 plus 0, well, this property is saying that the answer has to be negative 4, and it is. And you can picture that with the thermometer if you want. Minus 4 degrees, and then plus 0 means it doesn't get any warmer. So it's still minus 4 degrees. Makes sense. And then of course, oh wait, 0 plus negative 4. Well, 0 means it's 0 degrees, but adding negative 4 means it got 4 degrees colder. That makes sense too. Of course, it's going to end up being negative 4. 4 degrees colder than 0 degrees is negative 4 degrees. So that these things work with the thermometer as well. But the important thing to note is that it works, it makes sense, it seems obvious, it works with the negative numbers too. I think that's the important thing to take note of. What is my next one? This is one that I know the students know, and we talk about it quite often actually in our math lessons. The cumulative property, the writing is the long part, property, again, of addition. And now I'm lower on the chalkboard, so you know my handwriting is going to get messier. And this chalk is getting shorter. I'll need to change it soon. Cumulative property of addition. That is to say, I'll write it over here, a plus b is equal to b plus a. I told you would say it was obvious, but I don't want to do it with a's and b's. I want to try it with numbers. So that means, okay, what 5 plus 11 must be equal to 11 plus 5. It is something we already knew. 5 plus 11 is equal to 16, and 11 plus 5 is equal to 16. When you add two numbers, it doesn't matter which one you say first. 17 plus 1 is 18. 1 plus 17 is 18. It works. Does it also work with negative numbers? Let's find out. How about negative 3 plus negative 2? Is that equal to negative 2 plus negative 3? Yes. Negative 3 plus negative 2. Remember the rule. They're both negatives, so we add them together and the answer will be negative. Negative 3 and 2 are 5, so negative 3 plus negative 2 is negative 5. If I say the negative 2 first, that doesn't change anything. Negative 2 plus negative 3 is still adding two negative numbers. 2 plus 3 is 5, and they're both negative, so the answer is negative 5. So the cumulative property of addition works with positive numbers, which we kind of already knew. But it also works with negative numbers, which is, I think, the reason why it's good to mention right now, because all of these ideas will happen along the way, here and there, sometimes when you least expect them, while you're learning algebra. So that's the point. Now I have to erase. I've filled up a lot of space here, and I have some more properties. How much time do I have? That's the kicker. I have 14 and a half minutes left in my planned hour. The associative, these big long words. You'd think we were still in the geometry unit. The associative, no, it's not only in geometry that you have long words in math. The associative property of addition. Property. That D is sloppy looking. Okay, and what's that one? I don't want to write it with A's and B's. I just want to do it with numbers. And this is worth having some more examples. It's got a little bit more meat to it in the sense that there's just more for us to do and experiment with. It's a little bit more variety than the previous properties. So how about if we have 2 plus 3 plus 4? We'll do it way over here. 2 plus 3 plus 4. How would we do this? There's more than one way of answering this question, and I think we all know that. And right now I'm not talking about any negative numbers yet, but I will do some examples with those. I'd like to start off with the examples that only have positives. But now that we're adding 3 numbers, that's where it gets a little more challenging. There's more variety. But what can we do? I think lots of different people would have different steps going through their heads when they solve this problem. Easy as it is, there's different ways of doing it. 2 plus 3 is 5. That might be a step that a lot of us would do. But I'm also going to add 4. I have to also add this 4. And 5 plus 4 is 9. So the answer is 9. 2 plus 3 plus 4 is equal to 9. But one way of solving it is to say, I'm just going to do 2 plus 3 at first. Get their answer, and then I'll add 4 to the answer. But wait, is that the only way to do this? No. 2 plus 3 plus 4... What I could do is I could say, I'm not going to do the 2 yet. 3 plus 4 is 7. I'm doing the 3 plus 4 part first, but I still have to add that 2. So I end up with, of course, the same answer. And that's what the property is. The property is that regardless of which steps we go along the way to finish doing all of the addition that we're required to do, we're always getting the same answer. So is there a third way of doing this? Yes, not as easy to see maybe. 2 plus 3 plus 4. I could be a little contrary and say, I don't want to start with the 2 and the 3. That's too basic, that's too fast and easy to see for me. I don't want to start with 3 plus 4 either, that's also too basic. I find that just as easy. I'm going to do 2 plus 4 first. I'm skipping over the 3. 2 plus 4 is 6, but I still have to add the 3, and yes, I get the same answer. So the associative property of addition allows me to basically take any pathway I want through this problem, and I'll get the correct answer. And my answer is just as good as anyone else's answer. The pathway doesn't matter so long as you're obeying all the rules. And what rules were we obeying? 2 and 3 are both positive, so we add them, and the answer 5 is positive. So that's a rule we were just talking about a few minutes ago. We obeyed that rule though. And when we added the 5 and the 4, we obeyed that rule again. So what I haven't done yet is do examples of 2 things I haven't done yet. Thinking about how much time I have and how many more little topics I have. only a couple of small little topics, so I'm going to stick with this one a little longer. I like this one. It's fun. It's almost as fun as a factor tree. So one of the things I haven't tried yet is, well, okay, fine, we know how to add two numbers. We were doing that earlier. We do it a lot. And now we've proven, well, we can do it when there are three numbers. So let's try 4. So I want to try an example where I'm adding 4 numbers. I'm not trying the negatives yet, because that's the other thing I want to do. Involving negatives. And of course, there's more than one way to involve negatives. How about if we have 4 numbers? All of them are going to be positive. 1 plus 8 plus 11 plus 4. Haha, so randomly choosing any numbers I want, they're all positive. I'm able to add any two of these as my first step if I want. So 1 plus 8 is 9, plus 11, plus 4. And then I can say 9 plus 11 is 20, plus 4, and 20 plus 4 is 24. And of course, if I choose a different pathway, I'm going to get the same answer. 1 plus 8 plus 11 plus 4. I'm going to do 11 plus 4 is 15. And then I'm just carrying the 1 plus 8 part down. And then 8 plus 15 is 23. And I have 1 plus 23, and I end up with 24. Same answer. So I realize that there's a lot of different ways I can do this. And if I did one with 5 numbers, 6 numbers, 7 numbers, it would start being more and more and more different ways that I could get through the problem. And it's fun, and it's an easy property to apply. I want to do it one more time, though, just to show something. 1 plus 8 plus 11 plus 4. What if I decided? And of course, yes, you might think the next thing I'm going to do is 8 plus 11, do the middle two first. Yeah, I could do that, but I'm not. No, I'm saying 1 plus 8 is 9, and 11 plus 4 is 15. I did it. I did the 1 plus 8, and at the same time I did the 11 plus 4, and 9 plus 15 is 24. Whew! Still get 24, because the associative property works. Now let's try it. But I'm going back down to only 3 numbers, because I want to start sprinkling in some negative numbers. And just make sure that it still works. How about negative 3 plus 6 plus negative 2? Okay, there are 3 of them. And I can choose any. I know that the property works. I feel confident in it. I'm going to test it by choosing whichever 2. Okay, so whichever 2 numbers. I could start with the 2 outside numbers, the 2 left numbers, the 2 right numbers. I feel like starting with the 2 numbers over here on the right. So I'm going to just carry down the negative 3. And then I'm going to add the 6 and the negative 2, but slow down. Remember, there's a rule to apply when you combine with addition a positive and a negative. It's a positive and a negative, so I'm subtracting instead. And 6 minus 2 is 4. And then I give that the sign of the larger number, which was the 6, so it's a positive 4. So I'm going negative 3 plus, this plus went down here, negative 3 plus, it's positive 4. Now you don't really have to write the positive sign if you realize it's there, but watch out. Negative signs you should write, otherwise you will lose your negative sign and make a mistake. So negative 3 plus 4, and I'm doing the same rule. One's positive, one's negative. I subtract instead. The answer is 1. And which one's larger? The larger number was the 4, and it was positive, so my answer is positive 1. Does this work? I can even test it with a calculator. I don't know if that really counts as testing anything. I can even make it really easy with a calculator. And just see if it gives me the same answer. You have to learn calculators and integers. You have to learn how to use the key that makes a number negative. But I have negative 3, and the way that that's done can be different on different calculators. So I put in negative 3, and I'm adding 6, and then I'm adding negative 2. Positive 1 gave me the right answer, and of course I can take any pathway through. So negative 3 plus 6 plus negative 2. Maybe I feel it would be easier, and sometimes students want to do something in a way that's easier, which is okay. It's not always a cop-out. Yeah, you can do something the easiest way if you want. Sometimes it's the best choice. So I'm thinking I'm going to do the 2 outside numbers first because they're both negative. And I know the rule is if I add 2 negatives, the answer is negative. Negative 3 plus negative 2. 3 plus 2 is 5, so I have 5, and it's going to be negative 5. But I still have this plus 6. And now I'm doing that other rule. A negative and a positive, when I'm adding them, I subtract instead. 6 minus 5 is 1. And I give the answer the sign of the larger number, which was the 6, so it's positive 1. Same answer. It does work. A sprinkling combination of negatives and positives, the associative property still works. Worth practicing. 2 examples, not enough. Practice it a lot, because as you're doing algebra later on, you'll be in this position a lot where you need to combine 2 numbers with addition, and sometimes they're both negative, sometimes they're both positive, sometimes one's negative, one's positive. But not only 2 numbers. You will be in this situation a lot where you have to combine more than 2 numbers with addition. And some of them are positive, some of them are negative, sometimes they're all positive. There's all the different things that can happen. The associative property has your back. It's going to make sure that you're able to do this without getting too distracted by it and being able to focus on the thing you're actually working on at the time. That's what happens when you practice. And how am I doing for time? Less than 4 minutes left. I think I'd better stop with this. Would have liked to have done a few more examples, because it is a fun one. I find that a fun one. A little bit more to it than some of the other principles. Then there's the add with 0 principle. She knows it's almost supper time. I'm waiting for her to start standing up and wagging her tail and dancing with her front feet, because that's what she does. But I'm not saying her name. I'm not changing my voice into that cute voice you use when you're talking to a cute animal. I don't want to trigger it. I'm just kind of noticing in the corner of my eye what she's doing. Right now she just looks like a brown dust mop. Can't even see her eyes. The eyes disappeared again. Yeah, she went to the groomer. That was almost 3 weeks ago. Okay, can't see her eyes. Now, add with 0 principle. That is when you add a plus negative a. And I did see that. I did accidentally put that as an example way earlier in this lesson, and then I erased it. No, I'm saving that for later. Well, now is later. A plus negative a equals 0. Okay, yeah. I think it's easier to see when you use the numbers though. So a represents number. I'm going to use 3 plus negative 3. And yes, 3 plus negative 3 equals 0. So it's slightly different, right? We go to apply that rule that we were practicing. Oh, we have a positive and a negative and we're adding them. We subtract. Well, that's working, isn't it? Because 3 minus 3 is equal to 0. But then the sign thing feels a little different. We take the sign of the larger number. Well, neither of them's larger. They're the same. That's the point of this principle. So 0 doesn't have a sign. I'm not going to put a negative sign or a positive sign, because neither of them's larger. I kind of like that. There's kind of a beauty to that. And of course, if you write it backwards, it still works. Negative a plus a is really the same thing as a plus negative a. We kind of already talked about that as well. So negative a plus a is also equal to 0. So therefore, negative 42 plus 42 should be equal to 0. Here I am choosing big numbers. I'm becoming daring. Okay, and okay, what do? One's negative, one's positive, I subtract. 42 minus 42 is 0. Sign of the larger number, there is no larger number. The answer is 0. That's kind of cool. I like it more now that I've talked about it than I liked it before when I was just preparing my lesson plan. Maybe you have to talk about something out loud to really start appreciating it. One last thing, in very little time. Am I actually down to less than a minute? Yes. So I hope this last thing isn't too difficult. What is it? Actually, there are 2 last things, so I messed up. So I'm just going to not do one of them. Opposites. This is actually kind of useful. I kind of like it. It kind of has a way of just suddenly happening when you're in the middle of some math sometimes. So the opposite, using a bracket is the best way to show this. I'll write the word opposites. So 3 and I'm putting in a bracket, and then I'm going to put a negative sign before it. This is going to give me -3. Does it seem obvious? It just seems like I wrote a bracket I didn't need and then I took it away. Let's try doing it differently. How about if the number inside the bracket already has a negative sign and outside, is that going to change anything? No, that's not working at all, because opposite means I have to put the negative sign. The negative sign is what makes things become the opposite. Now it's making more sense. Okay, so the -5, the negative of -5, the two negative signs cancel, and I get 5. It's kind of interesting. So when I take away the bracket, the negative sign outside the bracket changes the sign of the thing that's inside the bracket to the opposite sign. So the inside the bracket here is positive, and once I took away the bracket, the negative sign changed that to -3. And here it was already negative, the negative sign changed it to positive. It's cool. I'm out of time though. In fact, I've even gone a little over my time. Okay, so I don't know. Okay, which things did I like the best? I know that the dog is only thinking of one thing, but she's still not, trying to get my attention. So she doesn't know what to tell time after all. I liked the associative property. That was a lot of fun. And I liked all those rules. I liked really thinking about those rules. What do you do when you add two positives? What do you do when you add two negatives? Or about one of each? The interesting stuff. And I still like the factor tree the best. I'm just going to admit it. And the dog is going to say goodbye. Oh, up you go. Come on. Up. Oh. Are you surprised? Did you not want your supper? How do you feel about supper? Oh, you do have eyes. Okay, so she's very excited about supper, and you'll be able to tell by the sound that happens when I put her on the floor. Okay, she's gone. All right, that was fun. Thank you very much for being here, and I think next lesson we're going to... Oh, she's back. Next lesson we're going to really get into some actual algebra stuff. We're ready. That's what we did today, is we made sure we're ready. I'll see you next time.